Κυρίες και κύριοι, ο κύριος Moritz Schubert. Okay, we are starting now? Yeah. Okay, good. Okay, thank you very much, Nick, for the nice introduction and for the invitation of the Hellenic chapter of ESCHUBERT to talk to here. I have to bring you all the best wishes from my boss, Dr. Christian Holter. He had planned to come here today to speak to you, but actually he's so busy. He was just coming back from a trip to USA, where we are just building a solar cooling plant, and another one to Central America, where a new big cooling project is coming. So he is actually at the moment very busy on this. And so this time he couldn't come. Hopefully he will come in one of the next years to this event. Yes, just to briefly introduce the company what I'm working for. It's called Solid. We are based in Austria, in Graz, in the southern part of Austria. We work on all activities relating to large-scale solar thermal systems, so no photovoltaics, no electricity generation, just heat and cold. It's we do project development for new plants. We design and engineer these plants. We do the construction of it, or at least the construction supervision with our experts. We do operation maintenance. For example, at the moment we have around 20 or 30 plants where we do the operation maintenance for. Either they are owned by our ESCO companies or by the customer. And we also offer financing, because often to build a large solar cooling system is a big hurdle to investors, to building owners. So we also offer this, that we finance the plant together with financial institutions, or in future also by crowdfunding. And we do research and development. That's a department where I also work in. And I will later show you a small project where we work on. Yes, Solid Group is based in Graz, not so far from Athens actually. And the yellow centers, the yellow are the countries where we are present. And here you can see where we have already built solar systems. So you can see the blue dots with solar cooling. They mostly stretch around the equator, starting from Arizona to Digital in Jamaica, to the Arab Emirates, Portugal, China, and Singapore, the biggest one. Yes, one of the research projects we are at the moment working on, we are working around 10, 12 research projects at the moment. One of the biggest on solar cooling is an Austrian one. It's called Solar Cooling Opt, where we first had a research project where we monitored several solar cooling plants, and now we have a bigger project where we go into deeper analysis and how to optimize these plants. And all this knowledge we gain on solar cooling, we also shared on the IEA, International Energy Agency, Solar Heating and Cooling Program. And here it's the task 48, the one which is actually running at the moment. Yes, to give you a brief insight into the technology which Solid use, probably you all have already heard on solar cooling. There are many different technologies which you can use for solar cooling. I give you a brief insight in the one which we use most, because for us it has proven to be the most reliable and long-lasting. Yes, what we always have at the Solid, it's a solar thermal collector field. where we heat, basically we heat up water. For solar cooling, we heat it up from 80 to maybe 95, 100 degrees. There are also other applications where we heat up water, for example, for boiler feed water, we heat it up from 15 degrees to around 95 degrees. So this is all possible with the solar thermal collector field, depending on how you design it. From there, the solar yield goes to a storage, sometimes a bigger one, sometimes a smaller one. Actually, for solar cooling, depending on the dimension, you can often nearly not use any storage at all. So you send the heat directly from the solar collector field to the absorption chiller, and from there you cool a building. Or you use the hot water directly without a cooling machine and supply processes which need heat, like industrial process or district heating. Yes, just to let you say a few words about the collectors we used. It's not the small ones which you know from domestic applications, which are normally around 2 square meters or maybe 4 square meters, but we use larger ones because they better fit the demands of a large installation and about the hydraulics and everything. I don't want to go too much into detail here, but these are special collectors which are more and more developed, and there are also non-concentrating collectors. You know, probably in order to reach high temperatures, high driving temperatures for absorption cooling machines, many use concentrating collectors which generate high pressurized water at 140 degrees or even steam. We do not so. We go for an approach where we say we don't want to have these things where you need tracking, where you have moving parts, where you might need cleaning of the mirrors and so on, because it's all a big issue and maintenance and so on. So we prefer to keep it simple and to use these flat plate collectors, which are quite highly developed at a high standard, but they are not as complex to operate as concentrating. So also a small difference between the collector which we use for the high temperatures and the standard collectors, which many of you know for domestic applications for hot water. So when you see at the left the standard collector and the right the high temperature collector, it has a second layer. Either it can be a Teflon foil or a glass, like it's a double glass, and it's at a thicker insulation on the back side. So what we also do on all our solar cooling systems and also many of the other large systems, that we have a telemonitoring, because our experience is that such a solar thermal system needs regular intervals of checking the operation. So it's and that we can best from our office to see the temperatures, if it still fits the demand. Also over the year, during the first year, you have to look during different seasons, different climate, if the plant is still operating in the way it was supposed to be. But of course, this doesn't replace the on-site maintenance, which also has to be done on all parts. So I give you now a brief presentation on the solar thermal cooling systems which we have already in operation. Or also still a few aspects on the technology. So yes, the driving idea behind the solar cooling is that we say the peak of solar radiation and the peak of cooling demand match perfectly. So in all hot climates, there's a lot of sunshine, and we can use this sunshine to cool the buildings. And even not only save some electricity, some megawatt hours, but also to reduce the connected power, the peak power demand, which is often the most expensive. So, is this a brand new technology? Solar cooling? No, it's definitely not. It was already introduced in 140 years ago in Paris. So yeah, these are the electricity savings which can be achieved by a solar cooling system. So you have including the heat rejection, which always requires the most energy, also for solar cooling. You still have a significant electricity demand, reduced electricity demand. So if you say on a long-term evaluation of compression cooling machines, you often end up between electrical COP or energy efficiency ratio between 2 and 3, and with a good running solar cooling system, you can, in theory, you could even go much higher, but in practice, it always shows that the cooling towers injection circuits normally needs so much pump electricity that to go beyond 10 is another big advantage is that this hazardous-free chiller liquids, this lithium bromide, is not as hazardous to the environment and has also not a climate potential like the conventional cooling machines, which do not operate on the CO2, and it also hasn't vibrations. So this is a very old cooling machine with my boss found operating in a university in the United States. So it's running now for over 70 years, and it is still operating. So because it's only a tiny solution pump, which is the only, and the rest of it is just steel parts, steel tanks in this machine. There's a vacuum in the machine which has to be renovated from month to month, from time to time, but otherwise it doesn't break down like other compression machines. Here I give you a small insight in the temperatures operated. So we say for absorption chiller machine, this absorption process is very sensitive to temperature levels. So we say on the cooling side, on the building side, it should be a building at a rather high cooling standard. So where you can go into the building at 14 degrees, at 7 degrees, or let's say maybe also 6 degrees, but it shouldn't require a cold water temperature of let's say 3 or 4 degrees, because here the efficiency would go down. And also it is very good if the building, if the distribution system can reach a rather high delta T up to, let's say, 14 degrees centigrade, or in Singapore, the one we installed, we can even deliver cold at 16 degrees. So, yeah, this you can see from these figures, a building like that needs to be quite well designed, but that's anyway what we recommend, that when you go for a solar cooling system, that you always also have to look at the distribution system, that you benefit from passive measures on the cooling load, that you optimize the cold generation system, and then when you've done this, you also integrate a solar cooling system. So this lithium bromide absorption chiller, it's normally driven at temperatures between 83 and 88, but you can also go lower than this. You can also go down to 70, 75 degrees, or if you want to run it more efficiently, you can also go to 95 degrees. But then, of course, the solar thermal collector field runs less effective at higher temperatures, so you always have to find a compromise between these. The cooling towers, we normally require wet cooling towers because the lithium bromide absorption chiller normally demands a return temperature between 28 and 30 degrees, and which is then heated up inside the chiller up to 35 degrees. Yes, this is another simplified working principle, as I showed you before, with the absorption chiller and so on. So yeah, here we can see the boundary between the solar cooling system and the conventional cooling system. I will show you later that we normally never use solar cooling only for building, but we combine it with the existing compression chiller. So both the compression chiller and the solar cooling tower feed into a common cold water storage tank, and from this cold water storage it goes to the air diffusers inside the building. You can also combine these absorption chilling machines with cogeneration units. So in countries which don't have a very reliable like 700 hours per year, you only need 30% of the installed load, or even 20 or 10. So as we have a rather high investment cost for our system, we say this investment cost can be the best payback if you have long operation hours every year, and this is reached when we go there where the part load is, with long operational hours every year, and the peak load, which is only a few hours every year, we say we leave this to the compression chillers because they are much cheaper to buy. Yes, now I will present you a few concepts on sizing a solar plant. Sorry. So yeah, there's this concept, we call it solar instant. So we don't have a big heat tank. So the heat which is generated by the solar collector field, it directly drives the absorption chiller machine. So yes, when the sun is shining during the day, you have cooling from the solar cooling system. But for example, in most countries, you want to have the cooling running into the evening also. So if you have enough space for a larger solar cooling system, you go for the other approach, which I will show you now. So here the red line is the cooling demand, which rises and which stays a bit high, also during the evening in many buildings, and the cooling, it starts in the morning. It has its peak in the between 2 2 and 3 or 4, depending on the orientation of the collector field. And when the sun goes down around 5, 6, 7, or the cooling declines. So we see here a gap which is not yet covered by the solar system. So, so I now present you the concept 2, where we produce a heat surplus during daytime, and it's stored for the night. So you can imagine it like this way. So here's again the heating demand, the same as we had before, and during the day we produce a surplus of energy which is stored and which is then used for the night. No. Yes, it's like this. And here, yeah, by the way, we don't use a cold storage or cold water storage, because a cold water storage has a rather low delta T. So maybe a cold water storage you can cool down from let's say 12 to 7 degrees, a delta T of 5 Kelvin. But when we use a hot water storage, we have a bigger spread. We can go maybe from 70 to, or let's say 80 to 95. So it's 15 kelvins. It's double or triple the temperature spread. And so we have only half or a third of the space demand for the energy storage. So yes, this is the reason here. You can see why Solid doesn't focus on residential applications, but only in large ones, because you can imagine also on pumps and so on. If you make them bigger, you have a lot of economies of size. Here I can show it to you quite nice at a chiller size. So when you have a chiller around 100 kilowatt cooling power, you can see the investment cost for the absorption chiller in Europe per kilowatt is around 3,000 or 4,000 euro. But beyond 100, it's on a logarithmic scale. So starting from 300, 500 kilowatt cooling power, the specific cost goes down a lot. So for a system of 1,000 kilowatt, the specific cost is only around 2,000 or even lower. When you say, or actually it's not only the chillers, the cost, it's the system cost. It's not only the chiller. On the chiller itself, it's even bigger, the economies of size. But on other parts of the solar system, for example, the collector array, you don't have so much economies of size. And the same applies then for the cold price. If you calculate it in euro per megawatt over several years, what you have on cost to produce cold water, you also benefit largely if you go for a big system. You can also see here the difference in the two concepts. So the blue dots are the solar instant, where we only use the energy which is produced during the day directly without a big storage. And the concept solar full day with the red dots, it requires these huge storages. So you see on each of these sides, it's considerably more expensive to go for this full solution. Yes, some points on the economics of solar cooling. So the payback depends mainly on the electricity rates and the peak charges. It's very different from country to country. Some countries charge the real price of electricity they have. Other countries have large subsidies. So in this case, obviously, it's more difficult to run it in an economic way, a solar cooling system. Also, solar radiation and meteorology, of course. So in these very hot areas with high irradiation, like in southern United States or in the Gulf states, or also in the Mediterranean area, it's of course the best. The economies of scales, what I just had told to you, and of course the financing environment. If you get green loans or other incentives or funding from the government and these things. And of course, what we learned even more, what we now nearly always go for, that we have an integrated system where we don't only use the heat from the collectors for cooling, but also for domestic hot water. For example, in the school in Singapore, they have a high demand on hot water for the showers. They don't use room heating because it's so hot in Singapore, and so here this hot water for the pupils and the boarding school where people live, it's a big benefit. And then yes, as I told you, the peak reducing concept, because each kilowatt you have connected power of electricity, it costs you a lot. And to use the solar panels in an efficient way, like we had just heard from our colleagues from Switzerland. If you build the building in an intelligent way, if you use the panels to shade the roofs, you can avoid the heat impact on the building by the irradiation. So now I'll give you a brief overview over the large solar cooling plants which we were operating in the recent years. So this is a small list starting around 10 years ago. You see in Kosovo, it's just a bit north here from Greece, not too far. We started with a system of 90 kilowatt. I will show you later, it's still running. And in the years after, we installed every year some system, and they got bigger and bigger and bigger. And in recent years, we installed systems with over 1,000 kilowatt of cooling power. Yes, one of the more recent installations is the one in the Sheikh Desert Learning Center. It's a very new building built in the desert of Abu Dhabi, and it hosts a museum. It was planned by architects from Austria, from Vienna, and with an engineering company from Vienna, we realized the solar cooling concept, where they have concrete core activation. So the driving temperatures for solar cooling machines, or the needed core temperatures, are not as high as if we feed into a ventilation system. And the cooling power is 400 kilowatt of the absorption chiller machine. Obviously, it's not enough to cover the whole building, but still this core activation, it can substantially contribute to this. Another one just built last year. It's in Jamaica, in the Caribbean Sea. It's a new building for the telecom company there, an office building. So they use the solar cold only for cooling of the building. And it's a machine of nearly 700 kilowatt cooling power. It says 1,000 square meters near the collector area. And here we could also see that it's very important that the cold distribution system and other the conventional compression cooling machine and the solar cooling machine has to be all commissioned in a very good way, because otherwise, if you don't match well the temperatures which the compressor needs, which the absorption chiller needs, which the building, which the inhabitants need, then you often run into discomfort levels, into too high electricity needs, and so on. So it's really important that when you start such a system, that you take them time and look at the parameters and adjust them to the way needed. So this is a plant in Singapore. I can show you briefly. This is a whole campus area. It's around 60,000 square meters. We can see collector area here. Here's also collector area, and here's a sport place. And left to the sport place, there's a collector area on the spectator stand. Then here's a swimming pool, and here on top is another collector area. The domestic hot water we supply, it goes from here by the residential building, from the boarding school, and the cooling machine is around here. So it's a huge distributed solar cooling area. All these collector fields from here to here and here, they all driven only by one pump and goes over one heat exchanger. So it's a large hydraulic circuit. It took us some days and weeks to balance all the flows in order to match the temperature requirements which we have, because we want to have these are several hundred of parallel flows. Each of these flows only supposed to have a certain delta T in order to run it the most effective, also not to have too high or too low pressure loss. So this was quite a challenge, but we managed it, and now the solar heat goes from the collectors to here, 2 tanks of 60 cubic meters, and then to the absorption chilling machine or to the domestic hot water. And it's now 2 years in operation, and it works quite well. It was surprising to us, the changing climate in Singapore. You know, it's around the equator, so it's supposed to be not too much changes all year round. But actually we have months with a lot of rain, next month a lot of sun, the triple of cold produced from one month to another. So it's really interesting how this climate there is. But at least we can say that we benefit largely from these flat plate non-concentrating collectors, because there's so much cloud during the day. So having a concentrating system, it would be very difficult to concentrate and to reach high temperatures and so on. Yeah, these are a few more pictures. Here we can see on this shaped building the collector area, and here's the main collector area, and in this part here these are all cooling towers. But cooling towers not only for the absorption chiller machine of the solar system, but also for the conventional machines. There are 3 compression chillers also in the building. Yes, there's more pictures on the solar collector field. Here the gray thing we can see, it's the absorption chiller. It's from the company Broad from China. It weighs around 10 tons, just empty the steel, and inside around 3 tons of solution of lithium bromide, a bit lithium chromide, and around 50% of water. So for the Olympic Sailing Village in China, we built already in 2006 for the Olympics, which took place in 2008, a system. Here we see 2 collector fields. this very nice one, but you see the collectors don't have always the same tilt, so it's difficult to reach here high temperatures. So we use this one for warm water, and this one with a better orientation, we use this one for solar cooling. It's a 910 kilowatt thermal power of the collectors, and they also use the district heat for cooling, the absorption chiller. Yeah, this gained the Asian Power Award in 2006 as being the best renewable plant in Asia. So here it's with the Arizona Public Service. It's a desert outdoor center where people can experience the desert. It's close to a lake, close to the town of Phoenix in Arizona. It is a very smart system. All the technology is in this small container, which we could prefabricate in Austria. It has a window you can see here, where you can see inside all the pumps and the cooling machine, and on top is the cooling tower. So it all went well when we started it 5 years ago, but just in the second season, because they have around 9 months of cooling demand and 3 of heating. So after this heating demand, we wanted to start the chiller again, and they called us in Austria and said, "Hey, there's a problem. We can't start the cooling system." So we had a look in our in the remote operating system, and we saw, oh, there's an issue with the cooling tower. We said to them, please have a look at the cooling tower. And then they looked into the cooling tower, and there was a family of birds breeding inside. They had there a nice place to stay. So we had to remove those birds, and from then it went perfectly again, the solar cooling system.
5 minutes, Mr. Schubert.
Okay, thank you. Yes, here we can see a very nice, so the climate of the dry desert climate of Arizona is just perfect for solar cooling, because they don't have a shoulder season like we have in Central Europe, where you have many months where you need neither heating nor cooling. But they have a very high heating demand in summer, and then it cools down, and from November, December, they have a significant heating demand, which we can, of course, also supply with the collectors, especially there in Arizona, because even in winter they have high irradiation. Yeah, another very nice project we have in Europe is in Portugal at the CGD bank. So there we were constrained on the collector area which we could use. So the architect didn't want to have us using the visible areas of the which you can see from outside, but we could only use those which you can see from an airplane. So the one which you see here with the white at the side. So these two and these 1, 2, 3. So 5 altogether. Each area is around 300 square meters. Altogether 1,580 square meters, and it drives a cooling machine as well as it supports the reheating system and the domestic hot water. Because you can imagine this building as a small town. This is 5,000 people every day coming there. It's 100,000 square meters. They have a hospital, theater, restaurants, everything. So therefore also good high hot water demand, which we can meet. So here, this is the system, and in the lobby they have a big collector to show their environmental efforts. Here on the terrace building, they have these cooling towers, also for the conventional cooling machines. And we also have a bit of freezing protection here in the fluid. Yes, one system here in Kosovo, in Southern Europe, Southeastern Europe. It runs very well, now already in the 11th operating season, even though the climate there is, or the technical environment, it was just built after the war. They had they sometimes have power cutoffs and so on, but our system endured all this. It's still operating. Our boss, or one of my bosses, goes there every year for maintenance, and so for an odd years he went there. He didn't have any major problems. It always runs very well, the system. So a few now I show you the biggest system which we have ever built, or which will also be the most powerful cooling system in the world. Solar cooling system, of course. It is the Desert Mountain High School in Arizona. It will get 5,000 square meters of collector area. So this will be put in this part of the campus. And so here I show you, these are some pictures of the constructions when they put these solar collectors over the parking. Normally we try to avoid this because it's very expensive, these steel structures, but in this case it worked out also because they needed a shading for the parking. And this is the way it looks now at the moment when the collector field is already finished. So we have this large collector area over the parking, and we have many collector areas here which are from the sports hall, which have the same tilt as at the sports hall. And on the flat roofs, we have elevated structures for the, or we have mounting structures for the collectors. Yeah, that's it. Thank you very much. I hope I could give you a good impression.
Thank you, Mr. Schubert. Ερωτήσεις αν υπάρχουν, παρακαλώ.
Thank you very much for your presentation. Is it possible, I ask you some precisions about numbers of the cost of the installation, the cost of the kilowatt hour, and in relationship with the cost of the electricity? You said before it depends, the cost of the electricity depends on the country. But have you some more precise numbers about the different installation you show us?
So for the cooling power, you can normally say the installation cost per kilowatt of cooling power, you can normally say it's between 800 and 1,200 euro per kilowatt cooling power which you install. Between 800 and 1,200.
Have you established a report between the consumption of electrical energy and solar energy in the different cases, in the worst and in the better, for example, in Arizona or in Austria, for example?
Yeah, in Austria, the biggest benefit of a solar system is always the hot water or the heating. But in Arizona, yes, there's I don't know the electricity figures which they have there, but with all the tax rules and so on they have, it's very economic to have a solar cooling system, yeah. Because, yeah, it's one of the highest irradiations in the world, and they have high cooling demand, so this is perfect environment for solar cooling.
From which size of installation this kind of installation is rentable,
yes, only
efficient? economic efficient?
Yeah, it should be more than 300 or 500 kilowatt of cooling power. So you need the area, you need more than 1,000 or better 1,500 square meters. So it's really huge buildings.
Another question.
I have two questions actually. First, what is an estimation of the annual efficiency of the thermal collector field? And second, if we were to substitute this collector field with photovoltaics and feed a normal air-to-water heat pump instead, would that be better or not?
Yeah, that depends on the components you use, but the solar thermal collector field has a very high efficiency. Normally you can say be around 50 to 60% over the year. So compared to the solar PV, which is normally around 15 to 20%. So it's around factor 3 or factor 4 more efficient, the solar thermal. But on the thermal, of course, you have heated as output from the collector field. In PV, you have electricity, so you can't compare it that easily, but still it's a very higher efficiency. And with the solar thermal, you also have the big advantage of the storage, so you can store surplus heat during the day for the evening, which for the solar cooling you need a battery, which is much more expensive than a hot water tank, which we can use. And what was your third question? Sorry. Okay, good. Thank you.
Μια τελευταία ερώτηση. One last question.
Have you ever tried a combined plant? That means high temperature, hot water to feed the storage tank, but instead of rejecting waste heat via cooling towers, use this surplus heat, this moderate low temperature quite enough to supply heat for such demand. Have you ever considered such a combined system or not?
Yes, we did, and you can also actually use it to because you can if you have to cool down the cooling water for the cooling tower, let's say to 30 degrees, and you have a heat exchanger, so you could heat up another water flow to around 25 degrees. So you could use this to preheat maybe domestic hot water, but for hygienic reasons and so on, normally you want to heat up the domestic hot water more than to these 25 degrees. So you need there another hot water system. And what you say is correct. The big challenge is to have the heat rejection in the best possible way. Some people try to use swimming pools to dump this waste heat, but actually this is very difficult because often when you have a cooling building, you don't want to heat up your swimming pool where you swim in, or where you want to have a refreshment. So this concept didn't really work out, but other ways, yeah, if you have everything, if you have a river or a sea or anything where you can cool down more efficient, it's for the solar cooling system. Yes.
Thank you very much, Mr. Schubert. Ευχαριστούμε.